Hi everyone, my name is Arya Sarpente and I'm here today to present to you the continuous work being done at Cranfield University to aid in space debris mitigation, namely Cranfield's family of drag augmentation systems. We're all here today because advances in small satellite technologies has allowed for an infinite possibilities of space mission architectures, supporting the diverse requirements of the space community and making space more accessible to all. Unfortunately, this increase in satellite activity has also led to an increase in space debris, adding to the already high number of objects in low Earth orbit. When we're considering mission architectures for exciting new missions, it's crucial not only to focus on the advancements in science and technology, but also to consider the sustainability of the spacecraft and the impact it will have on its environment. According to ESA's annual Space Environment Report, there are approximately 14,000 trackable objects in low Earth orbit and many more smaller untrackable objects. Involuntary collisions between operational payloads and space debris can have severe and sometimes catastrophic consequences. We want to avoid the Kessler syndrome, which describes a theoretical scenario where each collision generates space debris, which further increases the likelihood of subsequent collisions. The graphic that you can see on your left was taken from the Satellite Applications Catapult Q1 report published earlier this year. It shows the impressive growth of the small satellite launches to low Earth orbit over the past decade. Not only is this number of satellites worrying, but also the spatial density distribution of these satellites can pose a problem. An increased number of satellites at certain altitudes will have a more severe consequence than others. For example, it is generally assumed that natural post-mission re-entry within the required 25 years is guaranteed for satellites below an altitude of 650 kilometers, making this orbit a very attractive option for low-cost small satellite missions with limited deorbiting options. Another issue is that more than 50% of low Earth orbit payloads with an end of life in 2017 were not naturally compliant with the mitigation guidelines, and of those payloads, more than 70% made no attempt to be compliant. Therefore, it is clear that we need a system that helps to address these compliance gaps and helps us to operate our spacecraft sustainably. There are a number of approaches to removing a satellite from orbit, including active deorbit using propulsion, but drag augmentation systems can be an attractive low-cost solution for small satellites, particularly those without onboard propulsion capability. Failure analysis was previously performed at Cranfield University and concluded that the attitude control subsystem has the worst reliability of any subsystem, and its reliability decreases over time. This is particularly relevant for satellites that are relying on propulsive deorbit maneuvers, and therefore a passive deorbit method could be included in case of failure. Cranfield University has developed and qualified a family of scalable drag augmentation systems. These two systems, the Icarus and the deorbit mechanism, are simple, low-mass solutions designed to have a minimal impact on the host satellite, allowing them to be fitted at a late stage in the design. The devices require a brief current to deploy the drag sail, enlarging the effective area of the satellite, increasing its rate of orbital decay, and allowing it to re-enter and burn up within the Earth's atmosphere. The target market for these sails, are micro and mini satellites without onboard propulsion, but as mentioned before, they could also be used as a backup option for satellites with active deorbit. The image that you can see on your left here is the first drag sail that Cranfield built, the Icarus One. The booms are rigid struts, which are joined by tape hinges, allowing them to be stowed with the sail in a frame around the edges of one of the satellite's panels. Here we have a quick overview of Cranfield's drag augmentation system family. Icarus One was designed to be low mass, reliable, and safe. Emphasis was placed on preventing premature deployment of the sail and ensuring that actuation was under the control of the host spacecraft. It was also important to ensure that the sail would not produce any additional debris. Icarus One was launched on board TechnoSat-1 in July of 2014, and the sail successfully deployed 5 years later in April of 2019. The Icarus III was a smaller, simplified version of Icarus I. It was delivered to SSCL's Carbonite 1 in 3 months and adapted to an already mature satellite design. Compared to Icarus I, the reliability of deployment was improved by adding torsional springs to initiate deployment, and the sail folding pattern was simplified, allowing for a quicker stowing process. The satellite launched in July 2015, and the sail successfully deployed more than 3 years later in November 2018. Finally, we have the DOM design depicted in the bottom right corner. The DOM is a self-contained unit, significantly smaller than the Icarus model, and can be mounted on one side of the panel of the host satellite. Assembly time was improved by co-reeling the sail and booms around a central spool. Contrary to the Icarus model, the effective area of the DOM is not restricted by the satellite's side panel length, but rather by the booms themselves. The DOM was launched on board ESA's microsatellite Azael in December of 2018. Within the framework of ESA's Clean Space Initiative, CleanSat, Cranfield University took part in the technology assessment and concurrent engineering phase of the project. One of the outputs of this initiative was the top-level requirements of drag sail systems, which were then derived into our sail's design drivers. Several of these requirements, which we are now focused on verifying, are listed here on the left. These include ensuring the system is fully demisable, ensuring that the system is compatible with 10 years ground storage and still operates successfully after further 10 years storage on orbit, and making sure that the sail can achieve its expected performance in the harsh low Earth orbit environment. We are now looking to develop the third iteration of the sail, which is the hybrid design. The hybrid concept is a modular design, and it aims to further improve the adaptability of the system, allowing it to be tailored to a wider range of satellite configurations. The concept was derived from the strengths and weaknesses of the Icarus and DOM designs, and since the design does not require a full side of the panel of the host satellite for mounting purposes, protruding hardware such as antennas can be accommodated without impeding on the deployment of the sail. This beautiful picture here on the left was captured by Tech Demosat 1 shortly after sail deployment, and it confirmed the successful deployment of Icarus 1. Icarus 3 also successfully deployed in November 2018. Due to the consistent operations prior to sail deployment, we were able to quantify the effect of the sail on the satellite dynamics and found that the rate of change of semi-major axis doubled, which was in line with the doubling of the satellite's area. This slide actually displays those results. So on the top, you can see the change in semi-major axis decay. The red bar represents the deployment date itself. On the bottom, you can see the change in the satellite's B-star value. This value is the ballistic coefficient adjusted for atmospheric density, and it represents an object's susceptibility to drag. The scalability of the hybrid concept depends in part on the scalability of the DOM module. To assess this scalability, experiments were performed at Cranfield University using spring steel tape measures to simulate the C-shaped copper beryllium booms. Qualifying a product to be used in microgravity is expensive and intensive, hence over-engineering the product and testing it in 1G conditions was cost-effective. Currently, the DOM booms are 0.5 meter in length. They could not be considerably increased using the C-shaped cross-section in the current design, and after a series of experiments and trade-offs, it was decided to change the cross-section to a lenticular shape. This shape is made by having 2 steel shells held together in a polythene sheet. You can see this depicted in the first image on the left. Currently, the DOM deploys 4 booms simultaneously and symmetrically. The hybrid concept relies on using a different amount of booms in several different configurations, and therefore, to develop this concept, it was important to determine whether the DOM could still operate successfully if only 1 or 2 booms were deployed symmetrically or asymmetrically. The study concluded that the maximum length of boom before failure was 1.5 meters in a supported configuration where the booms were deployed on a table, and 1.1 meters in an unsupported configuration. These represent the lower limits of scalability of the DOM design as it currently stands. It also shows that changing the configuration and distribution of booms did not have any adverse effects on the deployment. To further assess the scalability of the booms, the maximum theoretical length of booms which could fit within the existing DOM housing was calculated. The relationship between increasing DOM housing, increasing the outer radius, and increasing the boom length was not linear. As can be seen from the table, increasing the outer radius from 38 millimeters to 48 millimeters significantly increases the maximum boom length without a significant increase to the overall mass of the system. As previously mentioned, we also concluded that the system is sufficiently robust to enable asymmetric and uneven deployment. The scalability assessment showed that the boom lengths could be increased from half a meter to 1.1 meter without changing the housing, the release mechanism, or the testing procedure. However, the size of the booms themselves increased disproportionately to their mass, and therefore the scalability of DOM depends not only on the physical limits of the mechanism, but also on the mass of the booms. As a weight-saving measure, lightweight composite alternatives were investigated to replace the copper beryllium booms. These composites were selected due to their high strength to stiffness ratios and the ability to tailor the properties of the laminates to optimize the directional properties for the design requirements. The DOM booms had conflicting requirements for their two configurations, stowed and deployed. For compact storage, reduced creep, and predictable deployment dynamics in stowed configuration, the laminate needs to have a high strain to failure ratio and a low axial Young's modulus. Conversely, in the deployed state, a high axial modulus is required to maximize the boom stiffness and to aid in reducing the very slender boom's most common failure mode, which is global column buckling. The optimal boom would have a collapsible tubular mass section, cross-section, made from thin ply materials to avoid inner flange buckling, and toughened epoxy, and an asymmetric layup of 2 to 3 plies in total. With this specific configuration, the composite booms will be a little bit over half the weight of the current copper beryllium booms and could be manufactured in-house at Cranfield University. Finally, I would just like to briefly summarise the findings from a UK Space Agency Pathfinder project undertaken by Cranfield University and Belstead Research Limited in March of 2019. The objectives were to assess the impact of the sail on the short-term dynamics of the satellite, the influence of the sail on the medium and long-term mission dynamics, and the effect of the sail on re-entry and demise of the spacecraft. Icarus 1 and Icarus 3 were both used as case studies for this project. The attitude prediction suggested that the satellite will enter a slow tumbling motion after passivation of AOCS and deployment of the sail. This was validated by observed data from DSTL's Daedalus observation campaign and publicly available TLE data. These results were further evidence that without a sail that's specifically designed to promote aerodynamic or solar stability, rapid transition into a tumbling motion should be expected post-sail deployment. The predicted medium-term impact of the sail was small for the power and communication subsystems of the platform, even when the AOCS is passivated and the satellite is permitted to tumble. Despite the sail deployment leading to an increase in system torques, if the AOCS were to remain active, these torques are expected to be within AOCS limits, and the satellite should be able to be capable of retaining control authority. This also suggests that the sail deployment could be brought forward in a mission, potentially significantly reducing the risk of mission failure before deployment is commanded. Finally, the re-entry is expected to be slightly steeper, with some preference to attitudes associated with aerodynamic stability, but these changes were not significant enough to result in a substantial change in the expected demise behavior of the satellite. To conclude, the drag augmentation systems developed at Cranfield University appear to be a practical and effective means for small satellites to operate sustainably. We've assessed the scalability of the system and their deployment dynamics, concluding that the length of the booms could be doubled without significantly altering the design of the mechanism, and operations could potentially continue after sail deployment, allowing for earlier deployment and thus reducing the risk of deployment failures. Looking to the future, we're hoping to continue our progress, improving our understanding of long-term material degradation in low Earth orbit and its effects on sails performance, and validating future low Earth atmospheric models with data from our deployed sails. Thank you very much for your time. I hope you enjoyed the rest of the conference.